became a thing since like really in the public opinion at least became a thing since release of ChatGPT. So we're gonna be exploring that and how kind of building our own ChatGPT actually by the end of the week. So this bit of introduction to this week. Kwai actually isn't here for this week. He's at New Zealand riding horses and skiing down mountains. So you've got us all for this week. So for today, we're going to be doing PyTorch. So we've done a little bit of PyTorch last week, I think Thursday and Friday, but you haven't really built your own kind of from scratch. And this is what the framework that all the researchers basically are using these days. So it'll be really exciting. And then Deepak will be taking us through a Kaggle competition. You guys will be working in teams to try to build the best network for predicting, I think, cirrhosis data set, right? Yeah. That'll be really cool. And then day 2, we're going to be going to word embeddings. We've already done a little bit of that, but really deep diving into how we started encoding words as just arrays of numbers in the pre-transformer world. And then in the afternoon, a bit of introduction on how transformers happen. So not really the math and the coding yet, just intuition of why it's so transformative. As far I didn't mean that, but yeah, why it's so important in the AI landscape. Day 3, rest day on Wednesday, which is good. And then day 4, this is like when it gets really, really cool. So we'll be deep diving into the architecture, all the matrix modifications, all the math, that will be what we're covering. And then in the afternoon, if we have time, focusing on just all the other ways that transformers can be applied. So it's not just text, which is what's really exciting, because anything that can be modeled as a sequence can use a transformer really. So I'm talking images, I'm talking voice. So really it is the basis that's going to be everything going forward. And then day 5, Brian will take you guys through building your own mini ChatGPT. So like literally the simplest minimal viable version. And this is actually something that is mainly derived from Andrew Karpathy's lecture. So he actually had to show this everyone. He's the founder of OpenAI and one of the head engineers at Tesla. And we're going to be using kind of his code on how to build one to build our own mini ChatGPT. He trained it on the Shakespeare, or like all works of Shakespeare, but I was thinking that we can train it on like our medical notes to see what comes up. So if you guys want to take your medical notes and like put it as a .txt file, and then we'll give you guys a drive link to upload it to. Just like try to give me as much data as possible, right? And I'd be curious to see like the simplest implementation, what's that going to spit out. Like, that would be pretty cool. Okay, and also, so that's basically everything this week. It'll be really exciting. And also, something to look forward to is that we've got some really cool guest speakers who are all going to be sharing a little bit about the deep learning and kind of this machine learning world. So do you guys know Jeremy Howard? Yeah, like he's an absolute legend. I think genuinely one of the most prominent AI researchers in Australia. He's done great stuff, and this slide does not even begin to encapsulate how much he's done. But he started really, in a very non-traditional way, that philosophy at Uni Melbourne before working at some consultancy place for a few years, and decided to learn coding and deep learning and all that. And this was before it was cool, by the way. So this was like really long ago. He founded fastmail.fm. So synchronized mailboxes are kind of like, obviously every mailbox should be synchronized across devices. But he was one of the pioneers of that. He was the president and chief scientist at Kaggle. He founded Analytic, which is a deep learning company focused on radiology mainly, but also just other ways that AI can help medicine. He has appointments everywhere in the world. Like, he worked at University of San Francisco, Stanford, Queensland, and is also working at Sierra right now. The thing that we know him most for is probably Fast.ai, which is the most popular course to self-teach this stuff, and also Answer.ai, which is a really high output research lab. And I literally just thought, wouldn't it be cool if Jeremy could come and speak to us? And I was like, okay, might as well send an email. And he replied, I think 12:30 a.m. and he replied 9 a.m. So it's crazy. So we're really excited. And we're going to have a form later so you guys can send questions to him, because he doesn't have time to write the slides, obviously. So Kwai will be interviewing him, and then we can ask questions to him. So this is really cool. Do you guys know Professor Meng Law? This? So TBA, he hasn't got back to us with time, but most likely in week 4. Yeah, but if he can't make it, then week 5. And you guys can ask him really case. Yeah, and he's an Australian as well, so that's really exciting. Okay, So Professor Meng Law is also just one of the coolest doctors I've ever met. He's crazy appointments as well. Professor of Neuroscience at the Translation Research, Professor, I think, Director of Intervention Radiology at the Alfred, and also Professor at Monash University, Professor of Electrical Engineering and Computer Systems Engineering. He directs his own lab at iBrain and has previously worked in the United States for a long time with appointments at the Mount Sinai School of Medicine in New York and the NYU School of Medicine. And he will be coming in person to us first week, so Monday of week 5. And you guys can ask him any questions and he will be giving us a proper talk. And then, I think I forgot to take a picture. Sorry, Sarah. So Sarah is she's currently a student here at Monash studying law and computer science. So she's really passionate about data security, and with AI kind of scraping the entire web, there's so much legal implication as what's allowed and what's not allowed, and the law is kind of still catching up. So she'll be giving us her perspective on how data security and kind of the law will intersect with the developing world of AI. So yeah, you guys can check out more on the website. So she's a president of MONSEC, the Monash Students Run Security Club, and also has her own website sharing her news and experiences. But yeah, that's not Sarah. Okay. And we got the most exciting part, a new segment. Because realistically, we got a new segment called Unpack with Deepak. So basically, today he will be helping us host a Kaggle competition, which is really exciting. Also, he will be sharing some just really cool, because he really follows the development of AI super closely and knows everything that's going on in the okay, but knows a lot of what's going on in the development of new technology. So he will be having a segment, just sharing what's cool basically. And then also, I think one of the prizes of the Kaggle competition is that you get to be a guest star. Is that correct? Yeah.
So if you guys come third or above, you get to join my segment. And then we can talk about something that interests you and interests everyone. So yeah, you got to work hard at the Kaggle game.
Exactly. You make sure to work hard.
Opportunity.
Okay, so with that introduction out of the way, hope you guys are excited for this week. We're going to start with PyTorch. And the first is why PyTorch. So basically, so far what we covered, so this is the transform architecture I've been kind of introducing every single day on one of my math stuff. So this is going to, it looks like just a clump of boxes multiplying together with some linear networks thrown in there. But this will actually make a lot of sense from maybe tomorrow actually. But essentially what we've got is that it's got so many parameters, like 1.8 trillion parameters, and it only gets bigger and bigger. And all the parameters we call just weights are numbers inside the matrix, right? So what we covered so far is Python is a universal language essentially of scientific community. We've done that. We've done linear algebra, which is what's really the engine that's powering all these models to learn and to predict and be so fast. We've covered calculus, which is how these models learn and improve over time. So now the last question is, where do you train them? And the answer is PyTorch. We're going to be using PyTorch, but some of you guys might have seen TensorFlow as well. If you go to the Kaggle machine learning courses, I think they use TensorFlow. But it is a bit outdated these days, and the two main advantages of PyTorch is that firstly, it gives the dynamic computation graph, which is really intuitive and easy to debug, and you can it's just a lot faster to have iterations over PyTorch than TensorFlow. And also, we just call it more Pythonic because it's designed for Python, and is really the syntax and everything is going to be really familiar to us, hopefully. And this kind of illustration of all the publications in terms of the dominance, in terms of what frameworks the researchers use. And this is a really good trend to see that, you can see that TensorFlow is going down and PyTorch is going up. And because all the new technologies, they're built off these kind of research, using PyTorch gives the best chance to do really well with the new technology and be able to understand their repositories. So let's get started. Oh, and also just one more cool slide is literally used by the biggest companies. It's actually developed by Facebook, but it is used by all the technology. So for example, OpenAI, they standardize on PyTorch. Tesla is pretty famous as well. They use PyTorch to power their self-driving cars. And you can imagine that most researchers as well, so not just researchers, the big companies also use PyTorch too. Okay, so we're gonna go through the first time we're gonna go through is a bit of scikit-learn and how that interacts with the neural networks that we're doing. So basically, this is the overall idea. There's 3 levels of abstraction when we talk about writing deep learning stuff. So the highest level is basically easy to use with minimal code. You don't need to get into the weeds of it. But the problem is you don't have as much control over your model. So the mid level is what PyTorch is at. It's really flexible, but a lot steeper learning curve to learn. And the low level is really direct interaction with hardware. So you guys might know that why NVIDIA is so powerful is because they got their GPUs in CUDA, which is basically the interface between the code and the hardware. So it makes your code run really efficiently. That will be low level that we won't cover into this course. It's a lot of engineering as well. But Fast AI and Scikit, so Fast AI is what Jeremy's made. Scikit is, I think you guys seen the notebook on week 1, day 4. But yeah, very easy to use. You don't need to get as much. You don't need to program all the backpropagation and all the gradient descent yourself. But you don't have as much control. And PyTorch and TensorFlow, the 2 frameworks that I covered before, will give you just a lot more control and make you do much cooler stuff. Okay, so in terms of scikit-learn, it's just really important to us because it is a high level abstraction. So it's a kind of a toolkit for machine learning and designed for beginners, right? But it's really good because we're going to be using that to go through the whole pipeline, going from data to analysis to predicting from data to testing your model. And we're not going to worry about the kind of specific, we're not going to worry about the implementation quite yet. Brian will cover that in a second. We're just going to focus on how it's done. So in terms of the 4 main steps, you start with the importing library and data set, you pre-process this data, you train the model, and then you validate and assess how good your model has done and kind of work on it. So you guys want to go to this notebook. Okay, did you guys get on the notebook? So don't worry about the PyTorch part in a second. We'll come back to it with this time. So I rebuilt the scikit stuff using PyTorch manually, but we're just going to be focusing on the scikit section for now. Okay, is anyone not on the notebook yet? Awesome. So the first part is importing libraries. Nothing much to talk about there. Basically the same thing. You can copy and paste this at the start of your notebook every single time. And the next part is loading the data set. So recall this function panda.readCSV. You give them the address that your file is stored relative to where you're at, where the notebook is at. And then you always want to peek inside the data to have a look at what it looks like. So data.head returns the first 5 lines. And it's really helpful because you can see what the columns are and the general structure. Kind of just get a feel of what the data set looks like. So what are input features from here? Do you guys want to, where's the mic? Okay. I'll pass the mic around and everyone answer a question like we did with calculus. You want to start? What are input features?
I don't know what that is.
Input features. So what are we going to be, so basically we're trying to predict the house value, right? So this is every entry is a suburb in, I think, California. And they give you, so the longitude, latitude, housing, median age, the median age of the houses, how many rooms in total, how many bedrooms in total, population, households, median income. And then you're supposed to use all that data to try to predict the median house value at a suburb. Okay, do you want to pass it on? So these are our input features. And recall that we can store every single data point as a vector, right? So bolded X refers to all this input. So X1 will be the first entry, that's longitude. X2 will be the latitude. X3 will be the median housing age. X4 will be the total rooms, total bedrooms, and so on and so forth. And in terms of output, that would just be the median house value. So you're trying to use all this and kind of find the relationship between all the inputs and try to map to the outputs. So that's what we call the y. And recall that there's no hat on that because y hat is our prediction, right? So y is the real, we call that the ground truth. Okay, so the first thing is we extract all the features of x and y. So what does capital X mean in this case?
I guess you're looking at the data.
Yeah.
So it's all the columns except for your output column.
Yeah, awesome. So basically, remember that I use lowercase x bolded. That generally denotes a vector. That's a single data point. But once we put it into a matrix, the convention is that we use the capital X. So that's what I got here. And remember how to access it. Access pandas is the same as NumPy. So the first column means that we want all the rows. Every single row is a data point. We want every single data point. And then we do comma, and then colon -1. That means that we're taking everything except for the last column. So we want to take the longitude, latitude, all the way to the median income. We don't want to take the median house value because that's what we're trying to predict in the end. So that means that y will be, we're taking all the rows again, we're taking every data point, and we're basically trying to extract the last column, which is what we're trying to predict, right? So that's what capital X is. It's essentially all the data points, but we don't know the final price. But the problem is not all data will be as simple as this data set. So I think this is one of the default Colab ones. So every single time you run Colab, Google will give you some sample data, and this is what that looks like. But there's a lot of things that we need to consider, and that might come into play in the Kaggle competition this afternoon. So first is, how do we deal with missing values? For example, if you're going to use longitude, latitude, all that to predict some value, what happens if something doesn't have, for example, one of the suburbs, they didn't collect the median housing age? Do you want to pass it on?
I'm not sure. I was wondering about that
Yeah.
over the weekend because you couldn't make it 0.
Yeah, if you can make it 0, that's true.
You can.
You can, yeah.
Wouldn't it affect?
Yeah, it will. So for example, remember how for linear regression, we're multiplying the input by a weight, right? And that weight is something that our network learns. Now, if there's 0, that means they will all be missing something, right? So that's not good. Yeah. Any other ideas? Feel free to pass it on as well.
Yeah, I'm not sure.
Ryan?
You can use imputation, so you can replace it with other values, like the mean of all the values.
Yeah, perfect. I think that's generally a bit more reasonable. So for example, if you don't have this, you'll be like, okay, whatever. Rather than using 0, which might affect input significantly, especially if it's a linear regression, we'll just replace it with the mean of this whole column, or the median. Okay, cool. What about comparing data from different sources? So, for example, there might be different scaling. Now, this is hard to show, but imagine something more subjective, like brightness or something. So, how much brightness one room gets might be different to when some other agency measures it with their own equipment, right? So this is an important part where if you get data from different sources, you might need to be scaling the data somehow. So for example, a really powerful technique we call standardization. So you will subtract the mean and divide by the standard deviation, so everything will be on the same scale. Do we need all the dimensions? Then pass it along. So do we need all the dimensions of this data set? What I mean by that is longitude, latitude, all the columns, all the features is a dimension. So something we also need to consider is, do we need everything?
Do we need to include
Yeah.
the different columns?
Yeah, do we need to include all the columns? What's the column? Are there any columns there that you'd be like, how does this affect the house price?
As we were saying, if there's certain columns that don't really affect the house price, then
Yeah, intuitively, it shouldn't affect the house price. I mean, personally, this is maybe subjective. I don't think longitude and latitude matter.
I was going to say more that's location, right? Location
Yeah.
affects house price a lot, right?
I guess it does, but like the problem with linear regression is that remember how we're multiplying the input to a weight. So that's like saying, you know, yeah. So for example, every single latitude you move to the right, your house price increases by 50,000, which doesn't make sense, right? Like definitely, you're right. Location does matter, but it's not like every time you move to the right, it just gets richer, or every time you move up, it gets poorer.
So if you want to actually because I assume you would want location ideally, and
Yeah.
it predicts house value. How would you go about implementing that?
Really good question. So sometimes we can do categorical variables. So categorical variables, or yeah, you can maybe group the suburbs into chunks, for example. So like, you know how we can, like, rather than doing the suburbs like Kew, Ball North, we can just be Burundara. That can be one chunk. So a lot less categories for you to deal with. Okay, awesome. Do you want to pass it along? What about the variables are categorical? So like this. Do you think house colors matter? If we also collect the color of the house.
I think the color matters somehow, right?
I don't know, like, do you look at the color? Probably, but okay. So how will we encode that though? That's the problem. Because it's not like we can make red 1, yellow 2, and green 3, right? That doesn't seem like makes much sense. That means that green will contribute twice as much to the value of the house as if it's a red house. So it may be, but it wouldn't be that kind of relationship. Any ideas on how we can encode this?
If I'm not mistaken, last week I talked about like one hot spot or something like that, like for categorical data, right? When you're doing like linear regression or anything, and there's an encoding way for like categorical data.
Yeah, awesome. Do you want to pass it along? Maybe not Deepak. Deepak will know. Pass it along. Next, we'll skip Deepak for now. So, what is one hot encoding?
I wasn't here for that day.
Okay, do you want to guess what one hot encoding might be?
One hot.
One hot, like just one and then hot, and then encoding.
My only guess is using emojis. So
Emojis. All right. Pass it along. Any guesses? Yeah.
Like when you, it'd be like if it was red, you might have a vector that's like 1, 0, 0. Where
Yeah.
the first number is red, and then that's like 1 or 0, and then the second one is whether it's yellow or not. So 0 means it's not, and then same for green.
Yeah. Awesome. So essentially, one hot encoding just means that there's only one thing that can be hot, right? So for example, see how here what I'm breaking down is I'm breaking the categories into different dimensions. So I'm having a dimension called red. That's one hot, right? So if it's like hot if it's 1, so it's on basically. So essentially one hot because I mean the house can only be one color at a time. So it's either red, yellow, or green. So if the red color lights up, it can't be yellow or green, and vice versa. Okay, so essentially we're adding 3 dimensions to represent. And the reason that, we'll talk about this tomorrow, I guess, but kind of our introduction is that that's what we used to do to vectors, to word embeddings before. Like imagine if you have a vocabulary of size like 10,000, right? And that's every single word you're trying to learn. One hot encoding would literally be like, maybe position 3,000 is the word hot. So it'd be like 0 everywhere else. And then there'll be a 1 at the 3,000th place. So imagine how bad this is. So there's absolutely no data on the relationships of the words, right? So that's what one hot encoding is. It's just essentially a vector that only has one thing that's on. So for example, this is a really cool step that you can try to stand out. Because if everyone's using the same model and in the competition later, realistically, like you guys, right now, there's not that many models we can do yet. So if you pre-process the data really well, that's how you can get really good results. So for example, there's so in the notebook I didn't do that. So mine was the simplest way possible. I'm thinking like surely these things shouldn't matter, or you can categorize them into like squares, right? Like there shouldn't be this if you move right or you move up or something that you get massive change to the house price. Yeah. So that's the introduction on pre-processing. There's so much to talk about here, but just get you guys thinking of how we might make the initial data a bit better. So let's get to the making the model part now. So what is this code doing here? Why am I doing models equal to capital linear regression? Do you guys want to pass the mic down?
Just like, I don't know,
just creating an instance of the. I assume linear regression is a class that's already been made by SQL,
Yeah.
and then you're just initializing that, and that'll have certain properties like dot fit or whatever, dot transform, I don't know, and then you can just use that to fit the model to the data.
Yeah, remember object-oriented programming last Wednesday is really, really important in machine learning because everything you'll be dealing with is essentially a object from a certain class. So the class that we're calling is called linear regression. So this has a lot of cool properties like here, like Peter was saying, the fit, and it can give you the weights inside, for example. So a lot of methods that we can do with this, and our model is essentially an object within that class. So this is kind of a quick revision on kind of what the model is doing. Basically, there is the weight that so the input, right? So this is like latitude, longitude. There'll be more inputs like the median house, the median number of rooms, population, median incomes, for example. They will add them all up, and then there's a bias as well that's added to every single house because we think that the kind of intuition here is that every house has some inherent value. So even if it has like really new or something like no rooms, not many rooms, or not many population, there's some inherent value to every single house just because it's some land that it sits on. So in terms of what we're looking to train is that we can only train the weights, right? So essentially our model is very simple because there's literally only 9 things to learn. It's W1, which is what multiplies the first weight, which is what multiplies to the first input, W2, which multiplies to that, so on and so forth. And there's also a bias term as well that's added to okay. But yeah, and also the bias term B, right? So this is what it looks like mathematically, and it's just a dot product of X and W plus a B at the end. So recall that Y hat, we denote a hat here because this is our prediction and not the ground truth. We'll be comparing this to the ground truth. Okay. So essentially, when we make the object called model, because we're using this class, there's already placeholders there for W and B, right? So this, you can imagine this class, it's got some slots in there that we can put in the weights after we learn it. So this is what .fit looks like. It's a method onto our object. And this basically, the reason I say that scikit is a high abstraction is because it takes everything in the hood, right? Remember how training, but there's so much math we need to do. But this, it just tells scikit to find the best weights and bias. So if we'll find the W1, W2, W3, and B, for example, that reduce the loss the most. And under the hood, you can imagine that the attributes, so the weights and biases, being updated to our model here. So remember, our model is just like a bucket that can have some way to store the weights and biases that happens to be the best after this .fit is applied. So you can have a look on the hood. So by the way, you guys can follow along with just run the things as we go to see what it really looks like. But basically, the model.coefficient, remember how it's got somewhere to store the coefficients, just the weights. So imagine that it's like y equals mx plus c, right? So this is the m here, the coefficient. It's what's in front of every input. And the intercept is the bias. So you can have a look and see what the real numbers are. So that's what it looks like. Essentially, W1 is this, W2 is that, W3 is that, W4, W5, W6, W7, W8, and then the B. So after we do that, so really this, everything we've done to this point is basically pre-processing, and the training of the model is as easy as making the model. So calling a model is a linear regression model, .fit, and you're done. Literally 2 lines to train this model. And obviously this is the simplest model, but there's a lot more complex things that you can train just off one step using the scikit library. And to predict, you can do model.predict x like this. So remember how x is the input. So essentially what this is that it will go through every single data point, and the W1, W2, W3 obviously are all locked in because our model has been trained. So after it's been fitted, it's done, it's frozen, right? And then x1 is the input of the new line. So for example, it'll be this. So it will, if we do model.predict, it will have a vector of, I guess of dimension 5 because there will be 5 different suburbs that it's trying to predict. Okay. Any questions so far? So that's a model already done in 2 steps. And what we're doing here is that data predict house value is essentially how we create a new column in pandas. So see here, we only have 9 columns, right? 8 for the inputs and then 1 for the outputs. And then we're calling a new column predicted house value. So this actually looks exactly the same as a dictionary. How to make a new entry in a dictionary, for example. And this is equal to yPredict, which is after you run model.predict. And then we can have a look at the head. So have you guys run that? How do you guys think this model will predict? Like, because it's very similar in regression. And any guesses? Not really good. And it looks so tragic. Look at this. So these are the first.
How does it get a negative?
So look, this is, I'm assuming like 66,000. It goes 7,000. That's like a factor of 10 off. This is respectable. Like, this is really good. This is supposed to be 800,000. It gets to negative 30,000. This is.
Fix the housing crisis.
Yeah. Get a house and collect $30,000 in cash. I'll do that. It's really, really bad. And I was really confused. I thought I did something wrong when I was doing this, but I couldn't find any mistakes. So I just decided to see how dot head is not the best metric because I haven't really looked too deep, but I'm pretty sure there's some like arbitrary ranking or like ordering in the CSV that we're not quite aware of. So I did random sampling. So if you do data.sample 5, it gives you 5 data points again, but this is a lot nicer. So this is a random file I got. It's not great, but at least it's in the same ballpark. Like, look at this one. 240,000, 250,000. Amazing. This one's respectable as well. This one's like 50,000 off, 80,000 off. So it's pretty respectable. And if you guys run a lot and sample, you actually see that it's decently respectable. You know, it's in the same kind of range. At least it's positive. So I'm not sure. So I haven't looked into it too much. But if you guys want to, try to go into the data set and see why, based on the ordering, why is it that the first few ones are so bad? I did like the first 20 and they're all having random values. But if I do sample, I hardly get any. I think there's 17,000 data points in here. I hardly ever get really bad values. But yeah, if you just do the first ones, it's really, really bad for some reason. So let me know if you find out why it's specifically bad for the first few. But yeah, look at this. So this is another sample. It's reasonably effective as well, right? Like 270,000 to 260,000. That's pretty good. Pretty good. This is really close. Like, this is all very respectable otherwise. And this is without any pre-processing. So I'm not even like, fixing the longitude and latitude problem. And maybe like households. Will that really affect the median house price? I don't know. Maybe median income will have a high impact. But yeah, it's a really cool demonstration of how this is what machine learning is all about, right? So you have a set of parameters that you want the machine to learn and it just goes ahead and learns it. So this is my question. Why are the first few so bad? Look at that. So this is the first 20, I think, but it's absolutely awfully wrong. Yeah, you guys can dig through data and try to figure it out if you want.
You care about latitude too much.
Maybe, I don't know. Like, that's why,
Like,
that's...
Your coefficients are your weights, right?
Yeah.
You see how like a second coefficient is like -4 e power 4. I think you care about latitude too much.
Yeah, right. So it's really docking points when it's so that is actually going up or like northwest? No, north south or maybe. But like this is like all of California, like counties or suburbs. And I genuinely think that there's definitely a trend somewhere. And the problem with this model is that it's trying to essentially the majority wins, right? It's trying to fit the majority, and maybe there's some relationship with it. I can imagine that close to the coast, like surely the house price will be worth more towards the Bay Area and all that. But yeah, there's definitely a better way to encode the latitude and longitude. Okay. So the mean square error, just to kind of a reminder, what I here is each individual row, right? Each data point, and try to add the y minus y hat, which is how far off your prediction is, square that, and then add it up to everything. Okay, so we've been going through this quite a lot. And you can see that it's got quite a bit of loss on average. So this is really cool because before we were just like eyeballing it. And you can see that some is respectable, some is really not. But yeah, when we have kind of this objective measurement of training loss, it's really good to compare different models. Okay, so before we move on, are we missing anything? So if you guys were training this, what else would you want to do to really check the accuracy of your model? Pass it along. Where's our mic? Lewis? Okay, what else would you do? Are we done? What else have we talked about in class sessions that we haven't done yet that could be helpful? Yeah, so are you worried about overfitting?
Sure. I mean, in class actually we have like a test set to evaluate things, right?
Yeah, so that's what we need, exactly, a validation set, because you can literally get zero, like if I make a 3-layer network, I can probably get like almost like zero loss on the training set, but then it would just be way overfitted. That would not generalize well at all. Not really a problem in linear regression because how overfit it's literally just a plane high dimension, right? How overfit can that be? Not really, but something to think about as well. But we always need a validation data set as well. So notice how we did the train. So we're reading the train data set. It's also, if you change it, you can get the test data set as well. I've done this at the end. So yesterday so this is linear regression. So essentially a 1-layer neural network, right? I've actually down below got a 2-layer neural network as well, just to see how much better it performs. That's built with PyTorch though. So after Brian's session, you guys should be able to make your own and really make as many layers as you want, which is pretty exciting, and play around with how many hidden neurons and try to get the best results.